Galileo Galilei in 1638 asserted that if you suspend a flexible cable or chain between two vertical supports, the shape will be a parabola. 20 years later, a 16-year-old Dutch boy, the soon-to-be famous mathematician, astronomer, clock designer Christian Huygens, showed this to be false. The correct solution was provided around 1691, independently by Johann Bernoulli and Gottfried Wilhelm Leibniz. In appropriate coordinates, the correct solution is the graph of a curve of the form e to the x plus e to the minus x divided by 2. This function is now known as the hyperbolic cosine function, written cosh x, C-O-S-H-X. There is a corresponding hyperbolic sine function, written S-I-N-H-X, pronounced sinh. The cosh of x is e to the x plus e to the minus x over 2, and the sinh of x is the difference, e to the x minus e to the minus x over 2. The graphs of sinh and cosh look like this. It is easy to show that cosh x is even while sinh x is odd. Just write out the definitions and it's perfectly clear. The domain of both sinh and cosh is the entire real line. The range of cosh is 1 to infinity. The range of sinh is the entire real line. Notice that for large positive values of x, the functions cosh x and sinh x look very much like 1/2 e to the x, since e to the minus x is 1 over e to the x and has limit 0 as x tends to infinity. The derivatives of cosh and sinh are easily computed. The derivative of sinh is the derivative of the ratio e to the x minus e to the minus x all divided by 2, and the factor 2 just comes out as a 1/2. So you're differentiating a difference of exponentials. Of course, differentiating e to the x gives you back e to the x. Differentiating e to the minus x by the chain rule gives you back e to the minus x times the derivative of minus x, which is minus 1. So you end up with e to the x plus e to the minus x over 2, which is the cosh. In the same way, when you differentiate the cosh, you get the sinh. Except for the presence and absence of minus signs, every formula for trigonometric functions has an analog for hyperbolic functions. For example, the well-known identity sine squared plus cos squared equals 1 has the analogous identity cosh squared minus sin squared equals 1. Proofs of the identities for hyperbolic functions are usually much easier than the proofs for trig functions, and in fact usually just involve straightforward calculations based on the definitions. For example, cosh squared minus sin squared is e to the x plus e to the minus x over 2 squared minus the difference over 2 squared, and when you write that out, you get 1. The addition formulas for trig functions also have analogs for hyperbolic functions. The sinh of p plus q is sinh p cosh q plus cosh p sinh q, almost identical to the formula for trig functions. However, cosh p plus q is cosh p cosh q plus sinh p sinh q, which is analogous to the formula for the cosine function, but uses a sum rather than a difference. The proofs of these formulas are quite straightforward, but very ugly. The easiest calculation is to start with the right side and reduce it to the left side. For example, start by writing sinh p cosh q plus cosh p sinh q, which is equal to enormous product and sum, the difference of the exponentials over 2 times the sum of the exponential over 2, plus essentially the same thing again. Multiply out this mess and simplify it and show that you get the left side. Please understand, no one expects you to memorize the addition formulas for the hyperbolic functions. What we want to emphasize is how to establish those formulas. The hyperbolic functions are defined on a basic hyperbola, while the trigonometric functions are defined on a basic circle. We don't want to make a major digression into proofs, but here is the fundamental hyperbola, which defines the hyperbolic functions, with, for your comparison, the fundamental circle for the trig functions. The fundamental hyperbola is defined by the formula u squared minus v squared equals 1, and you locate that point P on the hyperbola for which the shaded area is the number x over 2. Then we can show that the coordinates of that point P are cos x, sin x. Since this point lies on the hyperbola, it follows immediately, as we established from the definition, that cos squared minus sin squared is 1. Analogous to the trig identity, cos squared plus sine squared equals 1, representing the fact that the point cos theta sine theta is on the fundamental circle. There is also a hyperbolic tangent function defined, no surprise, as the ratio of sinh to cos. The hyperbolic tangent of x is sinh over cos, which is e to the x minus e to the minus x divided by e to the x plus e to the minus x. The derivative of the hyperbolic tangent, pronounced tanh, is again a straightforward exercise in differentiation using the quotient rule. The derivative of sinh over cos is, using the quotient rule, cos minus sinh over cos squared, but the numerator is exactly 1 by our fundamental identity. If we define, in analogy with the trigonometric functions, the hyperbolic secant of 1 over cos x, then we have just shown that the derivative of tanh is the square of the hyperbolic secant. The hyperbolic cotangent and cosecant are defined analogously. The hyperbolic cotangent of x is cos over sinh, and the hyperbolic cosecant of x is 1 over sinh. We can also define the inverse functions for the hyperbolic functions, and they turn up in all kinds of places, so we want to introduce them now. For sinh x, this is easy because it is clearly 1-to-1 from its graph. For cos x, the graph shows that this even function is not 1-to-1. So to create an inverse, we restrict cos x to the interval 0 infinity, on which it is clearly 1-to-1. The surprising fact is that we can actually give an explicit formula for both the inverse hyperbolic sine and the inverse hyperbolic cosine. Let's look for the inverse to the hyperbolic sine. X equals sinh inverse of y means that sinh x equals y, or e to the x minus e to the minus x over 2 is y. We need to solve this last equation for x as a function of y. Recognizing that e to the minus x is 1 over e to the x, you can write that last expression as e to the x minus 1 over e to the x, all divided by 2, equals y. And you can clean that up to get the equation e to the 2x minus 2y e to the x minus 1 equals 0. This is a quadratic equation in the positive unknown e to the x. To make this clear, let u equal e to the x, and recognize that u squared would then be e to the 2x. So our equation reads u squared minus 2y times u minus 1 equals 0. The quadratic formula gives us the solutions. U, which is e to the x, must be 1/2 the quantity 2y plus or minus the radical 4y squared plus 4. And when you clean that up, that tells you that e to the x must be y plus or minus y squared plus 1. The question is, which sign do we use, plus or minus? The fact that u equals e to the x must be positive tells us that we must use the plus sign. This is because y squared plus 1 is bigger than the square root of y squared equal to absolute y. So if we subtract the radical in our formula, we will get a solution u equals e to the x less than 0, which is not possible. Finally then, the solution to sinh x equals y is x equals the logarithm of u, which turned out to be y plus the square root of y squared plus 1. Interchanging the symbols x and y, we have the formula for the inverse of the hyperbolic sine. The inverse hyperbolic sine of x is the log of x plus the square root of x squared plus 1. You can compute the derivative of this inverse directly, or you can use our more general method, which we use for the inverses of the trig functions. For that method, you start with the identity that the hyperbolic sine of the hyperbolic sine's inverse of x is just x, identically. And you differentiate that identity to get that the hyperbolic cosine of inverse hyperbolic sine of x times the derivative of inverse hyperbolic sine of x equals 1, where again we've used the chain rule. Now use the identity cos squared minus sin squared equals 1 to write the derivative of the inverse hyperbolic sine of x is 1 over the cos of the inverse hyperbolic sine of x, and that's 1 over 1 plus the sin squared of the inverse sin of x, and that's just 1 over the radical 1 plus x squared. We can derive formulas for the inverses of our restricted hyperbolic cosine and for the hyperbolic tangent using the same principles. The resulting table of formulas for the inverses and their derivatives is given in the written notes. The important material here is not the final formulas, which you can always rederive or look up as needed. The important material is the derivations. We will use these principles involved over and over again in our development of the calculus.